In addition to hosting public data sets, we have an academic and research grant program. You can see the URL here, aws.amazon.com/education. And so with this program, we're actually funding a number of initiatives, things that are projects that are either going to have a significant impact on the world. If you think that you can help cure cancer, or you can stop the next influenza outbreak from having as massive an impact as it would otherwise, or if you have a new algorithm for finding stars outside of or planets outside of our solar system. All of these are projects that we have funded in the past. If you're developing new techniques or tools that would be generally useful for researchers in the cloud, you want to build a new file transfer utility that runs over UDP, doesn't lose data, and is secure. We've helped fund some of those development efforts in the past. If you want to create a set of machine images that could be generally used, if you want to create a way of automatically provisioning clusters that could be used for astrometric analysis or genomics workloads, those are other types of projects that we've funded in the past. And then also we've funded things like the SEG and Summer Workshop series that recently concluded at Caltech, where we provided infrastructure for all of the researchers to learn new infrared astronomy techniques and test these algorithms on the cloud. And then every researcher went away with access to the machine image and then continue to either use Amazon or run on-premise if they like. So encourage you to take a look at this program if that's of interest. Another thing that tends to come up with our research customers is that they don't want to use their credit card to pay for Amazon Web Services. And so what we have is the ability to invoice against a purchase order. And we can also link multiple accounts together. So if you have each department or even each researcher within a given department wants to create their own AWS account, we can send a bill actually at the university level or at the lab level, but also break out costs at the account level or even more granular than that, that allow you to do chargeback. We now have a web services API for generating CSVs and Excel documents that can be easily imported into billing systems. So it's becoming easier and easier actually to manage your spend within AWS and get the visibility that you need. We also have a way to create alarm thresholds. So if you're concerned about exceeding a budget because you're paying as you go, you can easily define rules that say, when I'm at 50% of a number X, send me an email. When I'm at 60%, send me a page or send me a text. When I get to 80%, trigger this workflow that might actually shut down my instances. That workflow you'd have to code yourself, but we have all of the tools that you need to develop that. We won't actually turn off your instances for you. We want you to make that decision, because in many cases, maybe you're exceeding your spend because your predicted spend because your research project's been wildly popular and you have a public outreach element to that, and you're getting word out of the success of your efforts. Or maybe you're a seismologist and you're part of the USGS, and there's been a recent earthquake and you're hosting there have been more earthquakes than normal in an area, and some more people are visiting your site, and so you actually want to get that information out. So any number of reasons that we don't want to turn off your infrastructure, but we give you the tools so that you can make informed decisions about how to respond to your spend over time. Wanted to talk about one of my favorite customers, NASA, and the many ways that they're using AWS now. Maybe first we'll start here in the upper left, with the Mars Exploration Rover program. So I already talked a bit about the workflow by which images make their way from Mars to the Amazon cloud, and some of the ways that researchers are using those. So in addition to spinning up a number of EC2 instances every time a transmission comes back through this relay using satellites from Mars to Earth, there's about a 2-hour period by which that researchers have the ability to generate the next sequence of commands. And before using the cloud, NASA Jet Propulsion Lab would spend about 80% of that time taking those images, stitching them together to generate a panorama, associating that panorama with other telemetry that was coming off of Mars Exploration Rover. And then about 20% of that finite period of time was given to the researchers to figure out, okay, what are we going to do? And then generate a sequence of commands that would then be transmitted back to the Mars Exploration Rovers. Because they can now automate that process and also spin up a large number of EC2 instances to generate the panoramas and do some of the other downstream analysis of that imagery and other telemetry. Now they're spending about 80% of their time figuring out what's scientifically interesting or hazardous as they generate those sequence of commands. And so, one, they're making more informed decisions about what to look at next. And two, they're able to actually generate longer sequences and go, do more exploration of Mars with every transmission back. Because this is an asynchronous system, they're only able to send a couple of sequences a day. So this turns out to actually allow them to get far more use out of the satellites of these rovers that take a lot of money and a lot of time, a lot of investment by teams of engineers and scientists to get these rovers safely onto the planet. And so the same systems are in place now for the Mars Science Laboratory, which is landing soon. A number of outreach-related activities, so helping the public understand how this Mars Science Laboratory is safely landed. These types of things will be running on Amazon Web Services. I wanted to talk now about the Deep Space Network. So one of the challenges that you can imagine with tons of satellites now actually even going beyond our solar system, but many missions in space at any given point in time using radio signals to communicate. It's very complex to manage the tracking and also the sequencing of when to communicate to a given satellite, given the asynchronous nature and the fact that relativity actually comes into play. So this, what you see here with the satellite dish on the left is one of the dishes for the Deep Space Network. The analysis of kind of and the scheduling of when to communicate to which satellite for how long and how to optimize for both transmission but also avoidance of packet loss is something that's now being tested in the cloud, and we'll use our high I/O instance types. The middle image that shows the plane is the Carbon in the Arctic Reservoir Vulnerability Experiment. So this mission is really interesting in that it uses both satellite and air-based resources to monitor the CO2 concentrations in the air column above the Arctic, and this is it's looking at how quickly the permafrost is becoming not so frosty and is seen as kind of the canary in the coal mine for climate change. And by measuring this, and actually monitoring this over a number of years, they're able to give indications of how quickly we're seeing global warming occur. And this mission is interesting in that it only costs about $5 million, including the satellite assets that were already in space at the time they're getting on those, the airborne missions that they're running, as well as all the compute that's occurring. And so by running in the cloud, they're able to minimize the amount of infrastructure that they need, but keep it as modern as possible. But by only running a large number of servers for a couple of hours at a time, every time they have one of these airborne missions, the infrastructure costs are far lower than they would have been with a more traditional deployment with dedicated data center facility and redundant servers that would have been sitting largely idle and in fact contributing to global warming because of all the power that they're consuming when they're not in use. And so by running in the cloud, they're able to extend their monitoring for much longer periods of time and actually have more airborne missions because the analysis component is so inexpensive. I'll also see here the Lunar Mapping and Modeling Project, which is creating GIS-type applications for both mobile devices or under PC, if you like, that allow you to overlay a number of interesting data layers on top of high-resolution imagery of the moon. There are similar projects for other planets, including Earth and our solar system. All of these tiles are generated in real time on Amazon based on the parameters that have been selected and streamed over the internet to the device that's actually being used to ask a given question. Lots and lots of other missions within NASA. I wanted to talk a little bit about Gaia. Gaia is a European Space Agency mission that's intending to catalog 1 billion stars and track those stars over a period of 7 years. And the idea is to look for wobble, which would indicate planets outside of our solar system. And so this problem is kind of an n-squared type problem, embarrassingly parallel application, and one that really benefits from running on Amazon. In that year one, they provision a very small fraction of the compute that they'll actually need in year 7 when they have many times the initial data set. they're also able to run their analysis very quickly because they can take advantage of the fact that one server running for 100 hours is just as expensive as 100 servers running for 1 hour. So as a result, they're able to get the results back from each of these 7-year surveys that they're doing of these billion stars and get that data in the hand of researchers as quickly as possible so that the downstream science is actually able to begin much, much faster.